Okay, now I want to just review a little bit about isomers. So we know isomers means they have same formula, chemical formula, but they are different structures. That means they are different molecules, but they have the same formula. So there are two types of isomers. One is the structural isomers, and other one is the stereoisomers. Structural isomers means they have the same formula, but their connections are different. They are connected different way, right? But they have the same carbon or hydrogen, oxygen, or any atoms, but they have all same numbers, but their connection is different. So we call that also constitutional isomers. We already talked about that. Now I'm going to talk about is the stereoisomers, and that means they have the same attachments, but their spatial arrangements are different. So we already talked a little bit one part of the stereoisomers. So I told stereoisomers, there are two stereoisomers are there. That is, one is called optical isomers, another one is called geometric isomers. Optical isomers means the molecules, the atom has four different atoms or molecules attached to it. As a result, its mirror image cannot be superimposed. So if you take the mirror image of a molecule, they are going to be different spatial arrangements. They cannot be impossible. So we already talked about that in our previous lecture. Now we are going to talk about the geometric isomers. We also call cis-trans isomers. Cis-trans isomers you can only find in double bonds. So if you have a double bond, and if that two double bonds has two different types of atoms, then these atoms can flip-flop and make a difference. So they have the same formula, but they are different spatial arrangements. Now we'll talk about more about this. Now before I was talking about that one, I want to talk about the free rotation around the carbon-carbon bond and a carbon double bond. So if you take a carbon-carbon single bond, you can see these two carbons has two hydrogen each and one chlorine each, right? So the two different, like they, you can see from the left to the right, you can see I can just rotate the single bond and I can make the other molecule. So they are going to be the same molecule, but it's the rotation will just change the spatial arrangement, but this rotation is always happening, so these molecules are going to be the same. But if you take a double bond which has one hydrogen each at the end and one chlorine each for the both carbon, you can see each carbon in this side, you can see the chlorines are in the same side. But in the other molecule, in the right hand side, you can see the chlorines are in the opposite side. So these double bond cannot be rotated and come back to the left molecule or go back to the right molecule. So they are different molecules. So they are having the same number of carbon, same number of hydrogen, same number of chlorine. But you can see the chlorines to both are in one side, in one molecule, and in other one we see the chlorine molecules are on the different side. So when the chlorine molecules are in one side, we call that cis, and if the chlorine molecules are the opposites, we call that trans. Okay, so you can also see in the molecular structure, you can see the green atoms, which are the chlorine molecules, are in the same side. They cannot be rotated as a double bond, so that is going to be different from the other one where the chlorine are in the opposite side. So we call that cis-trans isomerism, or we call that geometric isomerism. Okay, so this slide explains what we talked now. Uh, as a result, this when you have two groups similar into the carbon, if it is in one side we call cis, and if it's a opposite side we call that as trans. Okay, now when you talk about cis-trans geometry, we also can see the boiling point and the melting point. There is a difference in the boiling point and the melting point. You can see that, but the density is same. The physical properties are going to be same, but the chemical and the density is going to be same, but the melting and the boiling point is going to be different. Now we'll talk about the reactions of hydrocarbons. So we all know hydrocarbons mean we have hydrogen and carbon. They all undergo combustion. That means all these propanes, enes and ines can react with oxygen and form carbon dioxide and water, and it produces a lot of energy. So in the US, 90% of energy generated by combustion of hydrocarbons. Another reaction of alkane is the halogen substitution. So we replace hydrogen with a halogen. So we react with a chlorine or bromine molecule. In order to do this, you need heat or UV light. And instead of hydrogen, now you can see a chlorine in the position. So generally you get multiple products with multiple substitutions. Now we'll talk about the alkene and alkyne reactions. They will add molecules across the double bond, because the double bond can be broken and you can add molecules. First is the hydrogenation. That means if you have alkene alkynes, that means a double bond or triple bond, you can add hydrogen and you are you're breaking the double bond and adding hydrogen. That means we are making alkene. So we are making an unsaturated molecule into a saturated molecule. Next one is halogenation. That means we are adding chlorine or bromine molecules. So what happened? It will go and add into the hydrogen parts, the double bonds, as well as we can make halogenation, hydrogen halogenation. That means we are adding halogen with the hydrogen, like hydrogen chloride, hydrogen bromide, likewise. Okay, so when you are adding a molecule where you have polar and non-polar molecule, electrophilic and electronegative, electropositive molecule, then the electropositive will always will attach to the carbon with more hydrogen. Okay, now for example, now addition of hydrogen has no electropositive negative difference because it's a non-polar molecule. Addition of chlorine is a non-polar molecule, right? But addition of hydrogen halogenation, hydrogen and chlorine have an electropositive and electronegative compound. As a result, they can go and attack to a specific place only. So the electropositive part is the H plus will go to the carbon where you have the most hydrogen. Now we'll see how this reaction happens. Okay, now we will look at these reactions. Now here the first is chlorine is reacting with a double bond. So the chlorine will, each chlorine will go and attach to each carbon. Now here hydrogenation. So the hydrogen will go and attach to the double bond and form a single bond, and it's called hydrogenation. And now we are adding hydrogen chloride. So here hydrogen is slightly electropositive and chlorine is slightly electronegative. As a result, the H plus will go to the carbon where you have the most number of hydrogen containing carbon. So in this one, the most number of hydrogen containing carbon is the left one. So you'll see the hydrogen has attached to the left side and the chloride will go to the right side. So now we'll talk about the aromatic hydrocarbons. Aromatic hydrocarbons means they have benzene ring. So benzene ring has 6 carbons and they have 3 double bonds. And these 3 double bonds are not equal to normal double bonds, we have learned. And these 3 double bonds can resonance and form a hybrid structure. In this benzene ring, this double bond can rotate through this circle. As a result, we have to give a hybrid structure. There are 2 structures there. As a result, this double bond going around this ring. So we have to draw the whole circle inside the benzene ring. So this double bond is not equal to the double bond we are talking about. It's a little bit different. Okay, now we'll see how we name benzene derivatives. Now, first of all, when you are writing a benzene, like naming the benzene, like if you have only benzene and if you have something is substitute, we have to just name that substitute and write as benzene. Now, for example, if it's a halogen, we have to write the name like fluorine is there, but the N you had to put O, fluoro. For halogen substitution, we had to write as O. So we are showing it's fluorobenzene. If it's a chlorine, chlorobenzene. If it's a bromine, bromobenzene. And here you can see in the benzene you have these 3 carbons have come. That means if you have 3 carbons, what is the branch is called? Propyl. So a propyl branch is substitute to a benzene. So we call that propyl. We want a propylo because it's not a halogen. Okay. Now sometimes there are names for common benzene substitute. For example, if you have a benzene with a CH3 attached, we call that whole structure as toluene. If you have a benzene with amine attached, we call that aniline. If you have a benzene with OH attached, we call that phenol. If you have a benzene with a CH2HR, we call styrene. So have you heard about polystyrene? So polystyrene is made of styrene by polymerization. This double bond react each other and make a big polymer. So that's what is important to know these organic structure. Organic compounds are related to everywhere. Now we'll see benzene, how do we name as a substitution. So like if it's a benzene a subgroup. Now for example, now you can see this picture, the benzene is a subgroup, the other group is a big group because it has the alkene and you have more carbons there. So we cannot name only the benzene as a part and name the other part because it's difficult to name the other part with a double bond. Okay, so that main part is the carbon chain. So how many carbon chains are there? 6. So it's not going to be hex, but it's a double bond, so it's going to be hexene. But where the double bond is in the first one, so we put as 1 hexene. Now we have to name, okay, where the benzene is at the 4th place. So when you are naming a substitute as a benzene, we don't tell 4 benzene, no, we put as 4 phenyl. So we had to put 4 phenyl. Okay, so when benzene is a substitute, we call that as a phenyl group. Okay, now when you have more than one derivatives, how do you name it? Now for example, now you can see the first one where I have circle, you can see it's a CH3 with the benzene. So we know the CH3 with the benzene is a common name. We have a common name. We call that toluene. And in that common name, you can see there is chlorine is there, right? Okay, so if you have chlorine, so we have to make sure where the chlorine the position is. So we start the position by the main position. The CH3 is the main position, which is number 1, then go as 2, 3, 4, 5, 6. So you can see in the second position, you can see chloro. So we put as 2-chlorotoluene. We also can see here it is like in one position, first position it is CH3, in the second position it is chlorine. So we can also tell that 1, 2 positions. So this 1, 2 position as is being told as another name as ortho. So if you can say orthochlorotoluene. So toluene gives where the CH, well, there is a CH3 and what is the other one is the chloro, but it's in the ortho position. That means it's a 1, 2 position. In the 1 is CH3 and the second position is chloro. So if something is in the first and the second, we call as ortho, and if it is in the first and the third, we call as meta, which is the second one. You can see the CH3 is in the first position and chlorine is the third position. So so we call, if something is in the first and the third position, we call as meta, and if something is the first and the fourth position, we call as para. Right? So from ortho we put as O, or for meta we put as mem. Sometimes for para we put short name as P. Okay, now we'll practice this one. Here you can see this benzene has a fluorine and a chlorine group, so there's no common name for that. So we write as a substitute group. So you have a fluoro and a chloro group, and the number is like if you take fluorine as number 1, and then the chlorine is going to be number 4, and then if you take this one, then it has to be 1 fluoro 4 chloro benzene, but we had to put the chloro first according to the alphabetical order, so the answer is going to be 4 chloro 1 fluorobenzene. And for the other one, you have 2 bromine, so it has to be 1 3 dibromobenzene.